In this lesson, we will establish the m times L inequality. We will now develop the ML inequality, which is a useful tool for finding upper bounds for the absolute value of contour integrals of complex valued functions. So before we can establish the ML inequality, we need to prove the following lemma. This lemma will be used in the proof of the ML inequality. So the lemma says that the absolute value of the integral of Wt over the interval from a to b is less than or equal to the integral from a to b of the absolute value of Wt, W of t, where Wt is a piecewise continuous complex valued function. And t will be between a and b. So these were the first types of complex integrals that we developed a couple of lessons ago. So the absolute value of an integral of this type is less than or equal to the integral of the absolute value of the function. So for the proof, let's consider the first case when the left-hand side is equal to 0. Well, since 0 will be less than or equal to the integral of this non-negative function, it's clearly true. So the lemma is true if the left-hand side equals 0. It's also true if a equals b, because then both integrals will equal 0. So we're going to assume that a does not equal b, so a is less than b, and that the absolute value of the integral on the left-hand side is positive. We're going to assume that the absolute value of the integral from a to b w of t dt is positive and a is strictly less than b. Then the integral from a to b of w of t dt is equal to a complex number, and I'm going to write this complex number in exponential form. So I'm going to let this integral be equal to r0 times e to the I theta 0, which we're assuming is not equal to 0. So it's a complex number other than 0. So then I can rewrite r0 in the following way. r0 will equal e to the minus I theta 0 times the integral from a to b of w of t dt, and I can pull this exponential factor inside since this is an integral of the real variable t. E to the negative I theta 0 is a constant, so I have the integral from a to b of e to the minus I theta 0 w of t dt. Now notice that we started off this chain of equations with r0, and r0 is going to be a positive real number. So this integral that we just wrote is actually a real number, and so since r0 is real, we can actually write that this integral is actually equal to the real part of the same integral. So this is equal to the real part of the integral from a to b e to the minus I theta 0 w of t dt. And as we define these complex integrals, we defined the integral by breaking it up into its real and imaginary parts. And so the real part of this integral is actually equal to the integral of the real part of this function. So it's equal to the integral from a to b of the real part of e to the minus I theta 0 w of t dt. And now we're going to use the fact that the real part of a complex number is less than or equal to the modulus of a complex number. So we're using the fact that the real part of z is always less than or equal to the absolute value of z for any complex number z. So the integral we just wrote is going to be less than or equal to the integral from a to b of the absolute value of e to the minus I theta 0 w of t dt, but the absolute value of e to the minus I theta 0 is 1. So this is equal to just the integral from a to b of the absolute value of wt dt. So we've established that r0 is less than or equal to this integral from a to b of the absolute value of wt. To establish this lemma, the absolute value of the integral from a to b of wt dt equals the absolute value of r0 e to the I theta 0, which is equal to r0, since r0 is a positive real number, and we just established that r0 is less than or equal to the integral from a to b of the absolute value of wt dt. So this establishes the lemma. So next I'm going to state and prove the ML inequality using this lemma. Theorem. So the M times L inequality this theorem states that if f of z is a piecewise continuous function on a contour C, and the contour C has length L, so the length of contour C is capital L, and further we have an upper bound for f of z in absolute value. That is, the absolute value of f of z is less than or equal to capital M, so it's like a maximum, capital M for maximum, for all z on the contour C. Okay, so we have that f is piecewise continuous on a contour C, the contour has length L, and moreover, the absolute value of f of z is always less than or equal to capital M on the contour C. Then the ML inequality says that the absolute value of the contour integral of f over the contour C will be less than or equal to capital M times capital L. The absolute value of the contour integral of f will be less than or equal to the upper bound M times the length of the contour L. So for this proof, we're going to pick a parameterization of the contour. So let z of t for t between a and b be a parameterization of the contour C, then we have the absolute value of the contour integral of f over c using the parameterization. This will be equal to the absolute value of the integral from a to b of f of z of t times z prime of t dt. This is where we defined contour integrals. And now we can use the previous lemma to bring the absolute value inside the integral. So we write this as less than or equal to the integral from a to b of the absolute value of f of z of t times the absolute value of z prime of t dt. Now we're using our assumption that f is always less than or equal to capital M along the contour C. So this integral will be less than or equal to the integral from a to b of capital M times the absolute value of z prime of t dt. And since m is just a constant, I can pull m out of this integral. This is m times integral from a to b of the absolute value of z prime of t dt. And earlier when we looked at integrals of this type, we saw that from calculus we recognized this integral of the absolute value of z prime of t dt as the length of the contour C. And since the length of C we're assuming is L, this quantity will be equal to capital M times capital L. So therefore, the absolute value of the contour integral of f over c is less than or equal to m times L. So we'll see in the future that this ML inequality will be very useful when bounding contour integrals. Let's look at an application of the ML inequality. In this example, we're going to show that the absolute value of the contour integral over c of the function 1 over z squared plus 1 dz, this absolute value will be less than or equal to 2/3, where c is the line segment from 2, the real number 2, to complex number 2 plus 2i. Let's do a sketch real quick of this contour. So this contour starts at the real number 2 and goes up to the complex number 2 plus 2i. So here's our contour C. So now let's find a bound for the integrand, 1 over z squared plus 1. To do this, I'm going to first look at just the denominator. So for z on the contour C, the absolute value of z squared plus 1 is equal to the absolute value of z squared minus negative 1. I'm doing this so I can use the triangle inequality and write this as greater than or equal to the absolute value of z squared minus the absolute value of negative 1. So this is a corollary of the triangle inequality. Now, the absolute value of z squared is the same as the absolute value of z, the quantity squared, minus the absolute value of negative 1, which is 1. Now, if we look at z on the contour C, the absolute value of z will always be greater than or equal to 2. So if we look inside this absolute value bar, the absolute value of z squared minus 1 will always be we'll always have a positive value on the contour C. So this is going to be equal to the absolute value of z squared minus 1. And so I can drop the absolute value bars because this quantity is always positive. And moreover, since absolute value of z is greater than or equal to 2, this expression is greater than or equal to 2 squared minus 1, which equals 3. So we see that the denominator, z squared plus 1 in absolute value, is always greater than or equal to 3. So then the fraction 1 over z squared plus 1 in absolute value will equal 1 over the absolute value of z squared plus 1. And since the denominator is always greater than or equal to 3, 1 over z squared plus 1 absolute value will be less than or equal to 1/3. So if we make the denominator smaller, then the fraction gets bigger. So 1 over z squared plus 1 is less than or equal to 1/3. And the length, capital L, of the contour C is 2. Since the contour just goes from 2 up to 2 plus 2i, we have L is 2. Thus, by the ML inequality, the absolute value of the contour integral of 1 over z squared plus 1 dz over the contour C will be less than or equal to 1/3 times 2, or 2/3 as we claimed. Let's look at another example of the ML inequality. Now we're going to show that the absolute value of the contour integral over the contour C of z plus 4 over z cubed minus 1 dz, this integral is less than or equal to 6 pi over 7, where C is the following quarter of a circle. So this is a circle with radius 2, center at the origin. And we just take the portion of the circle in the first quadrant, so this quarter of a circle goes from 2 to 2i. So again, let's begin with a bound for the integrand. Let's consider values of c on the contour C. Well, absolute value of z plus 4 will be less than or equal to the absolute value of z plus absolute value of 4, which is 4. Well, on this circle, the absolute value of z is equal to 2. So this is 2 plus 4, which is 6. So the numerator is bounded by 6, and the absolute value of z cubed minus 1. Now, since this quantity is in the denominator, I want to find a lower bound for this quantity, so when I put it in the denominator, we can get an upper bound for the fraction. So the absolute value of z cubed plus minus 1, again, is greater than or equal to, by the corollary to the triangle inequality, the absolute value of z cubed minus the absolute value of 1. Again, we're dealing with absolute values of z equal to 2, so this just equals 2 cubed minus 1, and absolute value, 8 minus 1 is 7. So z cubed minus 1 in absolute value will be greater than or equal to 7 for all z on the contour C. Then the fraction, absolute value of z plus 4 over z cubed minus 1 equals absolute value of z plus 4 over absolute value of z cubed minus 1, and the numerator is less than or equal to 6. The denominator is greater than or equal to 7, so in the fraction, the 1 over z cubed minus 1 will be less than or equal to 1 over 7. So we get that the integrand in absolute value is less than or equal to 6/7. And now we need the length of the contour. So the length, capital L, of C. Well, the circle centered at the origin with radius 2 will have circumference 4 pi, but we're only taking 1/4 of this circle, so 4 pi over 4 is pi. So the length of this contour is pi units. Therefore, by the ML inequality, the absolute value of the contour integral of z plus 4 over z cubed minus 1 will be less than or equal to our maximum 6/7 times the length L pi, or 6 pi over 7.